Welcome back to the lecture series in the role of nanotechnology in agriculture, or the application of nanomaterials in agriculture. So, as of now, after the brief introduction about the current status of agrochemical use in agriculture and how we can minimize their use or optimize their use in order to meet the requirement of food production, fodder production, we moved on to the basics of nanotechnology, where we have already talked about the classification of nanomaterial in terms of their shape and in terms of their chemical nature. Followed by that, we have been talking about the different mode of synthesis, where we have talked about physical synthesis, chemical synthesis and biological synthesis. So, today we will invest a little bit more time on understanding some of these techniques and kind of overall outline of these techniques. So, if you recollect in previous class, this is where we started about the physical, chemical and the biological techniques. And the physical, I talked to you about application of mechanical pressure, high energy radiation, thermal energy, electrical energy, magnetic field, and which causing material abrasion, melting, evaporation, condensation, leading to the formation of nanostructures. And the very first technique we talked about is high energy ball milling. So, today we will talk a little bit about high energy ball milling first. What really is high energy ball milling? So, high energy ball milling, this is the very first technique. Okay. So, high energy ball milling, essentially what happens is that, say for example, you have this grinding ball which is moving in a particular direction and it is supported by other small balls out there like this. Okay. So, there is a grinding action which is happening, which you could see out here. Okay. And this whole thing is moving, and inside it you are having the grinding balls. So, the grinding balls are kept like this all over the place. So, this is the ball mill jar. And these are your grinding balls. And the material what has to be grinded now is being put here. These are the material which has to be grinded. Okay. So, basically it is a high energy ball milling system which has been represented out here, and now what we will be showing is the schematic representation of nanoparticle synthesis using high energy ball milling method with and without surfactants. So, this is the basic outline, and these are the particles which are the milling material. Okay. Now, when you are using surfactants or without surfactants, so the properties could be either these could be cationic material or you could have anionic material, negatively charged, or you could have something which is neutral, neither positive nor negative, and these are your bulk material. So, it could be anything, it could be even your nitrogen, phosphorus, big chunk of nitrogen salt, phosphorus salt, everything. Now here you are doing a mechanical grinding. Okay, while you are performing a mechanical grinding, what you are getting is a smaller part of the cationic particles which are positively charged, whereas negatively charged particles and neutral charge, but now the size has gone down. Now one option is that you do not use any kind of surfactants. So what is the role of a surfactants? Now this is one route where you are using no surfactant. So what the surfactant does is, these are small molecules which are inserted in between, which tries to keep these individual particles separate from each other. Of course, one has to ensure that the surfactant is not affecting the property or the major property of the nanomaterial, and that is why it is always essential the surfactant should be used in very least amount and should not be a bulky molecule, it should be a very small molecule, but it will ensure that nanoparticle is separated out from the, or nanoparticle does not, its properties does not gets modulated by the surfactants property. So if you are not using any surfactants, what you are essentially getting is a mixture of say something like this, just in a smaller dimension, and you have these negative anionic particles, something like this. This is what is the outcome. Now if you are using a surfactants, this is with surfactant. With surfactant, the story changes. You could have anionic surfactants when you are using an anionic. So I will just switch to the next page, that way we will get more space to explain the drawing. So if you are using an anionic surfactants, something like this. So the anionic surfactant will attract the cation. So you have the cationic particles like this, this. So you have the anionic surfactants like this. But one has to, as I am telling you, one has to ensure that this surfactants is not significantly influencing, the activity of the nanomaterial. Or there may be a situation where surfactant may help to modulate its properties, and that is what you are asking for. So you always have options what you are asking for. So it is in your control, it is a controlled synthesis. Okay. So this is the role of surfactants, and we will talk later as we will go in the applications that how the properties can be modulated using surfactants, and at times different surfactants may lead to different kind of crystal different resolution of crystal structures. You get better crystals with certain surfactants. With certain surfactants, the crystal structure is not very clean. So, and not only that, it also influences the effective action of the nanomaterial. The presence of surfactants further helps in drug delivery, that suppose I have to deliver drug onto a positive surface. So, that situation, these kind of delivery mode of surfactants may come out very handy, because the negatively charged cover will attract towards positively charged, and it may get a way to enter inside that particular delivery zone. So, the next, say for example, I do the reverse, where we are having cationic surfactants. So, when we talk about cationic surfactants, so these are all positively charged, and here you are having negatively charged nanomaterial, and on top of that you are having this positively charged cationic surfactants. Something like this. Okay. Similarly, you could have non-ionic surfactants, the third one, which is non-ionic. So, non-ionic surfactants are interesting. They personally do not have any kind of charge on them. So, what you are having is a situation like this. You have positively charged particles, you have neutral particles like this sitting out there, and now you are having this surfactants, which I am representing as in pink, something like this. So, in other words, you are creating some form of distancing the particle by putting some kind of surfactants, and surfactants are you use in your day-to-day life, where you are using different kind of material to reduce the surface tension. If you see soap, that's where you use the surfactants. Soap which should soak the clothes properly. So, when you mix soap in water, you are essentially helping it to cover the cloth very clearly, so that it could remove all the dirt from it. Okay. So, these are some of the very simple examples where post ball milling you can modify the nanoparticle by going through these kind of use of surfactants. Okay. So, this is what is called as your ball milling technique, high energy ball milling techniques, where surfactant molecule absorbed on the surface of the generated particle and help in lowering their surface energy by creating an organic layer on them, thus preventing them from aggregation. So, what are the roles of surfactants is this: prevent aggregation, this is important, then you are reducing the surface energy, as I have already mentioned. Further, it leads to the production of nanomaterial with smaller size range and with desired surface properties, size range. Okay. So, as we will walk through the course, you will see there are different places where surfactants have been used, and this is the basic of using surfactants. Okay. Now, the next technique what we will be talking about is inert gas condensation. So, inert gas condensation is one of the most primitive method of nanoparticle synthesis that employs, this is called, which employs inert gases, inert gas condensation. So, inert gas condensation is one of the primitive methods for nanomaterial synthesis that employs inert gas like helium or argon or liquid nitrogen, cooled substrate holder for the preparation of nanomaterial. The evaporated material are transported with inert gas and condensed onto a substrate attached to the liquid nitrogen. And basically these kind of methods are used for synthesis of different kind of nanomaterials. Okay. So, essentially this is one of the very old techniques where inert gas carriers are being used for synthesis of nanomaterial. It is something like this. Say for example, you have a substrate out here, okay, and you have here is a chamber having argon which is being purged into this chamber, and you have say iron, silver, silicon likewise, and there is around approximately 10 to the power minus 1 bar pressure out there, and this is called the aggregation zone. Okay, and then you have this aperture here, out here now C is your deposition section, that is out here, so what is happening is that substrate is sitting here, and so the carrier is carrying these particles and depositing it on the substrate as I was mentioning. So, this is the substrate and this is the nano cluster beam, and out here the pressure changes. So, if you follow it, pressure is continuously changing, and these kind of techniques are being used. There are 3 different steps. One is nucleation and growth, that is the first step. Followed by cluster collation, and lastly you are having coalescence. So, these are the 3 steps where inert gas condensation is being used, so to synthesize different kind of nanoparticles. So, if you look at these kind of techniques, by this time you must be realizing, as I was mentioning in the previous lecture, that much of these techniques are requiring pretty sophisticated tools and high temperature, high pressure. In other words, these are all high energy intensive procedures which are followed, but in the beginning these are the major techniques. Now, slowly we are drifting away. These are used of course for large scale synthesis or for specific purpose, but much of the biological applications are currently relying on much simple low energy intensive techniques, and which will coming, and there are reasons for it of not using these kind of techniques for synthesizing nanomaterials. Okay.